We've got a few talks, but in between the talks, we're going to have some time to chat and get caught up and nibble. So thank you everybody for bringing in food. So I wanted to give a little talk tonight about Apollo 8. This is something that happened. I realized recently that it's the 55th anniversary this month of this mission. And I was in grade 6 and I really wasn't I was following some of the space program, but not, and then this happened and I was hooked. And it was, who here remembers the Apollo 8, like experienced the Apollo 8 mission? A couple people. Mateo, you must remember the Apollo. So anyway, the thing about Apollo 8, and I'm going to get into sort of dig a little deep into the mission and the planning and everything. But some people argue that this was a bigger deal than Apollo 11. And I agree with them. Going to the moon the way they did in December 1968 was bold. And really, the engineers had pretty well thought that they had figured out everything and tested everything to a certain extent. Apollo 11 was built on 4 or 5 missions, but Apollo 8 was an incredibly amazing decision. And I want to try to express a little bit of that today. So, oh, I got a date wrong. It's May 25th, 1961. Already the talk is, I apologize. God damn it. So Kennedy, mainly for political reasons, decided that he would throw down the gauntlet on May 25th, 1961, and say, we're going to go to the moon by the end of the decade. And people assumed that that was at the end of 69, not 70, but really was the end of 70. But this was, again, a political move to sort of beat the Russians at something. So this was an interesting challenge, but made more so interesting because I've read some articles in early November 1963 about how Congress was ready to cut back Apollo and not land on the moon, but maybe go around the moon and like too much money and whatever. And then when Kennedy was assassinated, that was it. We were going to go to the moon by the end of the decade. And that was it. So that was the reason that we went to the moon as quickly as we did. So one aspect of Apollo is the contribution of Canadians. And the Avro Arrow was being built out in Malton in the late 50s and being tested. And then the mission, and it was an interceptor, basically for NATO and for Northern Canada missions, interceptor missions to protect North America. And the Diefenbaker government canceled that in February 1959. And our good friend Chris Gaynor wrote a book about how the NASA people in Langley, Virginia, who are working on the Mercury program, came up to Toronto to interview Avro Arrow engineers and essentially hired them down to go down and work on Mercury and ultimately Gemini and Apollo. And there were 35 of them, most of them Canadian, some English. So I'll tell you about how this book came around in a minute, but it was interesting how what effect and contribution these Canadians had. Some of them worked in mission control, they were flight directors. Some of them developed the heat shield on the command module. Some of them, one of them, well, I'll talk about in a minute. One of the people who was hired was Owen Maynard. Grew up in Sarnia, flew mosquitoes in World War II in England. And Betty and I got to know Owen quite well. And a really interesting guy. Couldn't stop talking. But really interesting guy. And he was essentially in charge of mission planning and ultimately became the chief engineer for Apollo. and is considered to be one of the fathers of the lunar module. So one of the things he did early on was to plan out, how do you get to the moon? In other words, how many missions do you need to fly to get to the moon? And he gave them letters, A through G. So A was to test the Saturn V rocket uncrewed, and that was ultimately done on 2 missions. B would be a test of an uncrewed lunar module in Earth orbit. C would be a crewed test of the command service module. And that's essentially just not the lunar lander, but just the spacecraft that would get you to and from the moon in Earth orbit for the duration of a lunar landing mission. So in other words, this spacecraft will get you to the moon and back. And so you have to make sure that it works for the duration of that mission. Mission D would be a test of the command service module and lunar module crewed in Earth orbit. And then there's a possibility of, they were thinking of doing a high altitude lunar module, command module mission, say out to halfway to the moon or that kind of thing, which they never did. And mission F was to do essentially a crewed mission of the command service module and the LEM in lunar orbit, which would lead you to mission G, which would be the first lunar landing attempt. So here's a picture of Owen with Tom Kelly on the left. Tom Kelly was Grumman's lunar module engineer chief developing and building the lunar module. So essentially, Tom and Owen are essentially the fathers of the lunar module. And I had an opportunity, I can't remember when, but anyway, Tom and Owen both have asteroids named after them because of what they did to contribute to that effort. Now, in 1994, there was a conference in Toronto from the National Space Society called the International Space Development Conference. Out near the airport, there used to be a hotel called the Constellation. And they had a whole bunch of meeting rooms named after different constellations, which was so cool. And that's where we had the meeting. And a few people from the Canadian Space Society knew Owen through, well, the weird relationship I had with Owen was that my father's secretary was married to her cousin. No, wait a minute. My father's secretary, her cousin was married to Owen. That's better. So she would tell me in high school, oh, you should meet my cousin's husband. He's had something to do with the Apollo program. And ultimately, I did meet him. And we had a special room at the hotel where we invited all these Avro Aero Canadians who worked on Apollo. And Chris Gaynor was there. And that's how the book came about, because he met all these guys and made contacts and whatever. But and there was an article in the Star about these guys. And then a few years later, Owen had an honorary degree given to him. And the fellow beside him is Jim Floyd, who was the chief engineer on the Avro Aero project. So that was kind of cool. So it's nice to give back to these guys who, you know, the stories that, well, amazing stories about what they went through for Apollo. Owen said that if Apollo 11 didn't land and then Apollo 12 didn't land, he would have quitted because his heart wouldn't have taken it. It just, you know, it was just amazing. This is a picture I took at the same event. And it's kind of a neat picture because that guy on the left is Chris Gaynor. So, and that's Owen's brother, his son in the middle with Jim Floyd. So anyway, his stories were pretty amazing. And then in 2019, Chris and I were asked to help design a stamp to commemorate the 50th anniversary, a Canada Post stamp to commemorate the 50th anniversary of Apollo 11. And so we recognized both Owen on the right and Jim Chamberlain, another Avro Aero Canadian who was fundamental in developing some of the Gemini program mission. So it's kind of neat to give back. And Owen passed in 2000. And he talked about his heart, his heart giving out over this and that. And ultimately he was in the hospital and his heart gave out. So amazing guy, and real pleasure to have known him. But he was the one that essentially was the chief engineer of Apollo, helped to design the lunar module, helped to plan all those missions. So the first mission of Apollo, this is an Apollo 8 talk, by the way, you remember that? The first mission, Apollo manned mission, was Apollo 1, and the prime crew sitting in the front there, White, Grissom, and Chaffee. The backup crew was Scott McDivitt and Schweikert, who ultimately flew Apollo 9. And it's interesting, in the early days, in all of the various companies where they were working on Apollo hardware, you'd see these signs, which were basically, do good work. Grissom gave this famous talk at one point at one of the contractors, do good work. And ultimately, you can only do so much. And here the crew are in front of pad 34, just a few days before they lost their lives in a fire in the spacecraft during a test. So that was a major setback of the mission of the program back in January 67. They were supposed to launch on February 21st, 67, essentially for the first test of the command module in Earth orbit. So essentially the Apollo program stopped at that point. It was an opportunity to rethink everything. Everything was going so fast. People were cutting corners, and it was a real opportunity just to rethink everything and to look at the hardware and the software and fix things. And a lot of people think that if there hadn't been the fire, then there would have been an accident in one of the early missions, given the quality control in the hardware. And so the fact that it happened on the ground probably might have even saved Apollo. So thinking back to those missions, the A, B, C, D, E, F, G, one of the first ones was to test the Saturn V, the large moon rocket. And that happened in November 1967 with Apollo 4. And it worked perfectly. It was like, what they did is that some of the earlier rockets, they would test the first stage and put second stage, third stage dummies. And Apollo, Saturn V, they just built the whole thing. They stuck it on the pad, they sent it off, and it worked perfectly. It was an amazing managerial decision. The second one, Apollo 6, flew a few months later in April 68, and it had all these problems. Engines shut down on the second stage. A third stage engine was supposed to relight. It wouldn't light. You can actually see little bits of insulation falling off this launch adapter where the LEM would normally be. You can see just bits were falling off everywhere. So this was a real surprise, and there were real concerns that they would actually have to launch a third Saturn V uncrewed to make sure that the Saturn V was ready to fly people. Meanwhile, the first unmanned, uncrewed mission of the lunar module was Apollo 5. This is LEM 1 being set for launch. They flew with no legs, no environmental system. It was just essentially a test of the LEM systems and the rocket propulsion. And it was launched on the Saturn 1B that would have launched the Apollo 1 crew. It worked pretty well. They had some problems that they had to really rethink through before they actually put people in the thing. But anyway, they got their mission off. Anyway, at this point, Frank Borman's crew, which would have been the Apollo 9 crew, to fly the second lunar module mission. His crewmates were Bill Anders on the left here, and Michael Collins, and that's Frank Borman there. So they were training to fly essentially the third Apollo mission, and their mission would have been to fly the lunar module out to a far distance from the Earth, just to test it. So Apollo, that unmanned LEM mission was in January 68. By the summer of 68, a few things were happening in the offices of Apollo in Washington and Houston. One was the LEM, the lunar module, was late. The LEM that people would fly in was not ready. It was not going to be ready by the fall of 68. And second, the Russians had this big rocket on the launch pad. And the CIA was telling people in Washington that the Russians might be thinking about sending people to the moon. And this was not acceptable to the administration at the time. They didn't want the Russians to beat the Americans. So they thought, okay, if the lunar module can't fly, we're going to fly the first manned Apollo mission in Earth orbit for a mission long enough to prove that the hardware works to get people to the moon and back. What about for the second Apollo mission, sending people to the moon without a lunar module? So that was the plan. So if Apollo 7 flew okay, there's the Apollo 7 crew. They launched in October 68 for 11 days. That was enough to easily get people to the moon and back. Then the idea would be to send a crew to the moon, Apollo 8, a few months later. The crew that was ready to fly the first lunar module, their commander was asked, do you want the mission to go to the moon? And he said, no, we want to wait and fly the lunar module. So NASA management went to Borman and said, what do you want to do? Would you take the moon mission without a lunar module? And Borman was a real Cold War fighter, beat the Russians at any cost. And he said, yes, we'll take the Apollo 8 mission. So the Apollo 8 and Apollo 9 mission astronauts flipped. So Apollo 7 flew in October 1968, proved out the systems on a spacecraft which could get to the moon and back. And here is the crew of Apollo 8 at the rollout of their Saturn V. So the first crewed Saturn V. And you'll notice that Michael Collins is no longer in the crew and Jim Lovell's there. Collins had to have minor surgery on his neck. So Jim Lovell moved into that spot. And kind of interesting, here's the prime crew of Apollo 8 with the spacecraft in the back, Borman, Lovell, and Anders. And their backups were Armstrong, Aldrin, and Hayes. And the way that it worked in Apollo is the backup crew skipped a couple missions and they would be prime. So at this point in time, the prime mission would have been, the prime crew of Apollo 11 would have been Armstrong and Hayes landing on the moon, with Aldrin being the command module pilot. And as we all know, that changed and Collins was moved back in there, and that's how Aldrin got his ticket to the moon, but that's another story. So here is the patch for Apollo 8, and their path to the moon's kind of a figure 8, and there's a reason for that. The spacecraft took off and headed to the moon in essentially an orbit that would pass in front of the leading edge of the moon, but be in a trajectory that if they did nothing, it would curve, the gravity would curve around and send the spacecraft back to home. So it was what they called a free return trajectory. So it kind of looked like a figure 8. Here's another nice diagram to give you an idea of what the mission plan was, launching on December 21st. And they'd go for an orbit and a half, and then they'd fire their engines to kick them off on a translunar coast for 2.5 days. They'd get into orbit around early morning of December 24th, Christmas Eve, 10 orbits of the moon, and then they'd fire their rocket again to come back and land back on Earth December 27th. So the reason that they had to launch around Christmas time was primarily because a good part of the mission was photographic. And Anders, who's the crewman on the mission, who was the lunar module pilot, who now didn't have a lunar module, they gave him all of the responsibilities of taking photos on the mission. So they wanted high resolution photos of all the landing sites for the future missions. So that's what his job was. And you want to have a nice phase angle of the moon. So new moon was around the time that they launched. So here's the first crewed launch of a Saturn V and their translunar injection to head them out on the way to the moon. The command service module separated from the third stage. And they had some planned television transmissions from the spacecraft, which were just awful. There hadn't been much effort to really create half decent television technology. And the first transmission, they tried to point it out the window and they couldn't focus on the moon. And, you know, obviously there were other things to train for and plan for than television, but they did send a few television transmissions back on the way to the moon and on when they were in orbit around the moon. Not very good views of the moon, but there was everyone was watching. It was just amazing to see these people halfway between the Earth and the moon sending back TV. Meanwhile, Jim Lovell's job was the navigator, and he essentially spent all of his time looking through the telescope and the sextant of the command module. And essentially what he would do, it's an amateur astronomer's dream. You had to find certain stars and line them up in crosshairs and then punch buttons and tell the computer what you were looking at and when you were looking at it. And then that would update the navigation and guidance system in the computer. That information would be sent down to the ground. But then also there was a manned spaceflight network navigation system where they had 3 major big radio antennas where they could track the spacecraft. And they had to have the 3 of them because they had to have something where the moon was above the horizon all the time for one of these tracking systems. So with the manned spaceflight network and the updating of the navigation system on the computer, they were able to navigate to and from the moon. And from that information, they would fire their main engine in their service module, or they would fire, if necessary, just their little reaction control engines. But that gives you an idea of how big their spacecraft was. That's Frank Borman sitting in the left-hand seat. There's the middle seat, and the person taking the picture is the right-hand seat. And down to the right is a lower equipment bay where Lovell would be looking through the telescope. But that's it. So it's like 3 people in the front of a SUV for 8 or 9 days. So to get into lunar orbit, they fire their engine to slow down, be captured by the gravity. So that happened on Christmas Eve, I mean. Now, the Earthrise photo is kind of an interesting story. Anders was taking photos of the moon at certain craters, and he had a flight plan that he had to stick to, you know, exactly. He only had so much film, and people wanted certain photos of certain things. And then at one point, and it's interesting, they always have this tape recorder going inside the spacecraft to catch the audio. And so if you listen to this, Anders says, "Oh, look at out there, the Earth is coming up. And where's the camera?" And Anders grabs it, and Borman's been really, I don't know, he's a bit of a, I don't know. He wasn't very nice to Anders. He said, "Oh no, those photos aren't planned for." And here's this amazing photo. And he takes a photo and realizes that the Hasselblad has a black and white film mag on it. So with the Hasselblad, you can put in a dark slide and take the mag off and put on a color one. So here's the picture that he first took of the Earth rising. And then by the time he got the color mag on, that's Africa sticking out there. And by the time he got it, he got the photo that we're all familiar with. So it wasn't planned, it was a surprise. But they did take some excellent photos of the moon. But after just 10 orbits, they had a TV program where they actually read from Genesis. and NASA got sued by a few people because of that. But anyway, it was they headed back home, and this is the view they had of the moon, and of course Mare Crisium there in Ingranus. So a lot of the near side of the moon visible, but a lot of the far side as well. And December 27th, they were back. So again, the Saturn V had flown with problems. The command service module had flown successfully, but we all know from Apollo 13, it was nice to have a lunar module backup when your command service module fails. But it was a mission that was extremely bold and probably made the lunar landing possible within the next 12 months. If you know a little bit about history, 1968 in the US was not a good year with Vietnam demonstrations, 2 assassinations, a presidential election, which saw a really bad Democratic convention in Chicago. And they just, it was a great way to recover the year. And Borman always in his talks commented on a telegram that they received to the crew, which was basically to the crew of Apollo 8, you saved 1968. So Borman passed away just recently, and Anders and Lovell are still alive. But their mission made the next 2 missions, Apollo 9 to fly in Earth orbit, and Apollo 10 to fly in lunar orbit, made Apollo 11 a success. Thank you.
Okay. Yeah, sure. Go for it. So first of all, thanks, Randy, for the Apollo 8 talk. I love your Apollo talks, and I made a rookie mistake tonight. I said I was willing to go second, but never follow a Randy Apollo talk. That's a rookie mistake. So I reached back in history a little bit. We were looking for another talk, and I said, Randy, well, if they're not bored of listening to me, I can go back and pull out some stuff from the archives of my experiences around the 2 transits. Many of you probably saw one or both of those transits in Ontario in 2004 and 2012. I understand the weather here cooperated reasonably well. And I think the club had an event right here on campus, right? Was it? It was here for the 2012 one, and over 1,000 people came out to look through club telescopes, which must have been a fantastic outreach event. So, okay, good. Yeah, great. So many of you will have good memories of one or both of those transits already. I'm going to explain a little bit about what's going on with transits, and then talk a little bit about my experiences in different parts of the world from Ontario. I was traveling with my company, living abroad with my company, Ford, for about 19 years straight, including both of those transits. So I was in different parts of the world, and I'll share a little bit about my experiences. So we'll talk a little bit about the definition of a transit real quick, and kind of the frequency of Venus and Mercury transits. I've got a slide or 2 on the scientific importance of transits through the 16th, 17th, and 18th centuries and 19th centuries. And then I'll get into a little bit around my experiences in 2004 and 2012. So first, a definition of the transit. Probably everybody in the room already knows this, but transit occurs when a small body moves in front of a larger body. And from Earth, we can see planetary transits across the sun of both Mercury and Venus at the right times and the right circumstances. So this is just a typical example of a Venus transit. The planet comes in from the left. You get a first contact, or sometimes called exterior contact, as it touches the disk of the sun, and then it moves on to the disk. Once it's fully inside, you've got second contact, or sometimes called interior contact. And then it'll keep moving across over a span of a few hours, and then exit at the far side. I think typically the Venus ones are about 6 hours long or so. And then when they exit, you have another interior contact, often called third contact, And then when it's just still touching, but almost completely done and outside the sun again, is fourth contact or the exterior contact. So the frequency of Venus and Mercury transits. So the Venus ones are extremely systematic in their timing. And this diagram kind of shows that. Hopefully you can, this thing is kind of in the way a little bit here. Control, Alt, Shift, H. Oh, wow. Now, so, oh, that'll go away too. I thought I have to do another one. Okay. Okay, good. So here you get a feel for the transit. So typically the Venus transit comes in pairs, about 8 years apart. And so you can see going back to the 1600s, there's only been, 10 of them since then, or 8 since then. And we're waiting now for the next one in 2117. But you can see a very systematic cycle here, 129.5 years between the first of the pair and the next first of a pair. And then 113.5 until the next first of a pair. So over 243 years, you'll have kind of 2 sets of this, and you'll have 2 pairs. So there was a pair in the 16th century. So back about this time, Kepler was predicting when transits were going to happen, which still blows my mind that somebody back in the 1600s could figure that out and predict with pretty good certainty when a transit was going to happen. A pretty bright dude. So he predicted that one was going to happen on December 7th, 1631, but he died before it could happen. And I think from the books that I've read, I think that one was largely clouded out across most of Europe, and that's where most of the astronomers were in those days, were in Europe. And so there's not really any recorded observation of that transit. But the next one, 1639, was observed by 2 guys, Horrocks and Crabtree, and they had optical aids and a telescope, and they are widely recognized as the first humans to see a Venus transit with an optical aid. So successful in 1639. We'll talk a little bit more about the history in a minute, but there were 2 more in the 17th or the 18th century, 2 more in the 19th century, but they were so late that there were none in the 20th century. And then the 2 that we'll talk about at the end that all of us witnessed were in 2004 and 2012. So the next one is in 2117. I'm pretty confident none of us are going to be here to see that one. Matteo, you might be around. You never know. Never know. You might have a hard time seeing through the telescope, but you might be around. So just in case you're wondering if this presentation is a total waste of your time because you're not going to see another Venus transit. Yeah. As very old senior citizens. Yep. So just in case you're completely discouraged or you think you're going to waste your time completely, I threw this slide in. Mercury comes to the rescue. So Mercury transits happen more frequently. I think it's because the planes of the orbit of Mercury and Earth are lined up a little bit better than the planes of Venus and Mercury. Plus Mercury is closer to the sun, and that makes a difference too. But they happen more frequently. I have at the bottom here, I can go into the detail, but there's a series of kind of cycles, and those cycles can have Mercury transits 6, 7, or 13, or 20, or 33 years apart, but very systematic, just like the Venus ones. So the next 5 transits are all Mercury transits, and we're in a little bit of a dry spell at the moment. So we're in 2023. The next one is November 13th in 2032. So that's about 9 years away. But right after that, there'll be another one 7 years later, and another one 10 years after that, and another one 3 years after that, and 10 years after that. So over a few decades there's going to be 5 opportunities to see Mercury transits. Most of us, probably saw one. I saw one in 2016. I think there was another one a couple of years later, maybe in 2018 or so. But like I said, we're in a dry spell now. We've got to wait a little while, but we don't have to wait for a Venus transit to see a transit. So historical and scientific importance of the transits. So the reason transits were scientifically important and drew a lot of attention from astronomers down through the centuries is trying to get a feel for the distance to the sun. That was the whole thing. It was a very good opportunity to try to estimate that distance. And I'm not going to try to explain the details, I probably get it completely wrong, but the concept here is that if you have 2 observers of a transit on Earth and get them pretty far apart, like at least a radius apart, And if they both observe the same Venus transit, and if they take very careful readings of the time that the transits begin and the position of the transit across the disk of the sun, and measuring some of those angles, if they collect all of that data with fairly good accuracy, then astronomers in those days would use trigonometry to try to calculate the distance, because they knew the distance between these two spots on Earth pretty well. If they knew that and they knew all the angles and had all the measurements, they could use trigonometry to get a measurement on the distance to the sun. And that was really important. So here's a lot of words here, but I'll just kind of talk it through. You don't have to worry about reading it. But up until the 17th century, astronomers had reached the point where they had a pretty good sense of the scale of the solar system. They had a pretty good sense of relative distances between the planets. They had a pretty good feel that this planet was 5 times further away than this planet, but they didn't know how far away this planet was, right? So they didn't have a measuring stick that could help them get the scale. And then they could say, okay, if that's how far that planet is, and that one's 5 times further away, now I know how far that one is, right? So that's what they were missing. And so everybody was trying to key in on trying to get that measuring stick. And the distance to the sun, the astronomical unit, became that measuring stick. If you could get an accurate measure on that, then you could get a pretty good feel for how far away is Mars, how far away is Jupiter and Saturn and Uranus and Neptune, right? So that's why it was so important. So Kepler stepped in around that time and predicted that if you use the Venus transit in 1631, well, he predicted the transit, as I mentioned. He predicted the first transit, and then he died and didn't see it. And as I mentioned earlier, Horrocks and Crabtree saw the 1639 one, which was the second one in that pair. But then we get to Edmund Halley, who lived between 1656 and 1742, and another extremely bright dude. And he proposed that if you did exactly what I just kind of described in that previous diagram, you could probably get a pretty good feel for the distance to the sun, that astronomical unit. And he also predicted that probably a Venus transit would be better for that purpose than a Mercury transit. And I think the reason for that is that Venus is a lot closer, so the angles will be a lot easier to measure than Mercury. Plus, Mercury is extremely tiny. For those of you that have seen a Mercury transit, it's a tiny, tiny dot crossing the disk. A little harder to measure the exact time of those first, second, third, and fourth contacts for a little tiny Mercury, right? So he was right about that. The Venus transits they're the way to go if you want to try to get that astronomical unit. So but of course he died before the next ones came around. So he admonished all the scientific community, you got to try this. Here's how I think you should do it. Here's how I think it'll work. I'm not going to be around, but try it on the next pair. So in 1761, a bunch of scientists tried it, a number of trips around the planet to try to do this. And there are some books, I'll give you the titles at the end. There's some great books on the expeditions for these Venus transits. In those days, you didn't just get on a plane. You know, you were talking, in some cases, years to get to the location you needed to be, and then it would be clouded out. Like, it's just like the hardship that these astronomers went through on these Venus transit trips. But nevertheless, some good attempts made for the 1761 one. I'm just going to back up one sec here. So we're in these ones here, the 1761 and 1769. And then it got refined with these two in the 19th century, quite a bit closer. So I'll just go back. So in 1761, astronomers estimated the range to the sun at about 125 to 159 million miles. So fairly wide range, but the real value is in there. So they captured the real value in that range. 8 years later, many trips planned by astronomers from many different countries, including James Cook, led an expedition down to Tahiti. Scientists did the work, but he led the expedition to Tahiti. But that one, the scientists they were ready. They were all over the world trying to get those disparate locations to measure the Venus transit. And they got the distance to 153 million miles. And that's getting much, much closer and not near as wide a range. In the 19th century, those two that happened in the 1800s, further refinement, and they got it down to 149.59. And then the real value that spacecraft would measure today using telemetry is 149.6. So Halley was onto something. It was a method that could work well if you had the patience and the endurance to make it work. But there are some great stories of hardship of astronomers trying to get these measurements from really difficult places to get to in the world. Okay, so the 2004 Venus transit. So at the time, I was living in Japan, working for Mazda. I was living in Hiroshima. So I was in the part of the world that was going to see the transit in progress at sunset. And you guys were over here where you would see the transit in progress at sunrise. And I think some of you went down, probably watched it come up over the lake in those days. So I was in Hiroshima. My kids were going to an international school. And so I thought it would be really, really cool to try to show them the transit. So here's a drawing of that particular transit. Venus was going to cross on the southern end of the limb of the sun, moving from left to right. And from my location, I would see the first couple hours of it until it set at sunset, and then I would miss the rest of it. So that's the conditions that I was going to see it in. So I thought it'd be really cool to try to give all the kids in the international school an opportunity to see a transit. So I made this page up and provided it to the principal and all the school, all the teachers. And the timing was going to be, late afternoon before the buses come. I was going to have all the classes come out. So I gave them instructions. I told them to tell their kids not to look at the transit when they come out with their eyes. They have to only look at it through my telescope. I was as prepared as I could be. And my plan was to have all the kids just cycle through really quick and see a Venus transit, probably the only time in their life that they would ever see it. Well, best laid plans. It poured all day long. It just rained cats and dogs in Hiroshima, Japan, all day long. So that never happened, never came together, but it did give me a little bit of an appreciation for these astronomers that would spend, a year and a half getting to a remote site in Australia or Africa, and then it would be clouded out. They had some tough times. So, but it wasn't cloudy everywhere, and many people here saw it, which is great. Here's a shot that Fred Espenak took, just a time lapse of Venus moving across. And then here's a NASA photo taken from a spacecraft, probably in hydrogen alpha and maybe some other filters on the sun, but a phenomenal photo of that Venus transit. So I made a vow to myself after I got rained out on that event. I said, 8 years from now, I'm going to be on the driest, most cloud-free, arid place I can find on the planet, because I am not missing the second one. So that was my vow made on June 8th, 2004. So now fast forward to 2012. And where am I living? I'm living in the UK. So I don't know about you, but the UK is a fantastic place. I spent 5 years there with Ford over a couple of tours. I loved it, but it does not meet the definition of the driest, most cloud-free, arid environment on the planet. So I started looking around for options. And of course, England would have been in this section with the progress, transit in progress when the sun comes up. So I started looking around. Here's the climate map. So sure enough, the climate map indicated that there's probably a 50 to 70% chance of cloud cover in the UK on a June 5th, 6th, typically. But I looked down here and saw this yellow spot and saw Egypt. And Egypt looked like it would have less than a 10% chance in a summer month like that, June 5th and 6th, less than a 10% chance of cloud cover. So I thought, okay, that's where I'm going to be if I'm going to keep my vow. So I found a resort in a place called Marsa Alam. This is down here. There's a lot of fancy resorts that cater mostly to European tourists. But that resort I figured would work pretty well. I'd be on the beach, and I would be facing east from the beach, and I would see the sun come up over the Red Sea with Venus already on it. So that was my strategy. And the other advantage of going down to Egypt was it would give me about an extra hour. So for both these locations, England and in Egypt, the sun was going to come up with the Venus already in progress, and then it would finish. So the time from sunrise in the UK, I would have been 4:49 sunrise, and the final stage would have been 5:54 fourth contact. So I would have had about an hour and 5 minutes to see of the transit, the last hour and 5 of about a 6-hour event. Whereas from Marsa Alam, the sun would come up at 4:53 over the Red Sea, But the eclipse wouldn't, or the transit wouldn't be done until 6:33. So I'd have about 2 hours. So I'd get about a quarter of the transit seen from there. So that was another reason for wanting to go down there. So the resort itself was beautiful. And of course, there was not a cloud in the sky, probably most of the year there, I would think. But certainly on the time that I was there, I didn't see a cloud at all. Beautiful resort. And the beach, was going to be perfect. But by then, disaster had struck. So I mentioned that a lot of astronomers had faced lots of adversity when they were doing their trips. So I had some too, and it was all self-inflicted. So I had planned the flights myself. I planned the flights myself, and I must have got a little confused on the timing of the stopover in Cairo. Because I'm on that plane flying to Cairo, and I'm looking at my tickets and I'm realizing, geez, I've only got like 15 minutes to get to the next plane once I touch down in Cairo. And I thought, how did I screw this? How did I screw this up? So I talked to the flight attendant, and they called ahead, and when the plane landed, they let me get off first. I was way near the back, but they talked to everybody and said, this guy's got to get off fast to make his plane. So I went flying off the plane. They ran me through the airport, and they got me to the second plane. I got on the plane to Marseille, all good. But of course, my checked suitcase was not going to make that transition in 15 minutes, right? That just wasn't going to happen. And I knew that. I figured no problem. They'll just send it the next day. But then I got to Marseille, and they told me that the next flight from Cairo wouldn't come until the 7th, which was the day after the whole transit was done. And in fact, it was the plane I was going to use to fly back to Cairo in, was coming, on the 7th. And so I had the clothes on my back, and I had my small carry-on with some of my optical gear, but I was missing a lot of stuff. A rookie mistake. I had a lot of equipment in a check bag. I've never done that again since. So I was pretty crushed that night because I'd put a lot of time into practicing and getting all the equipment and gear together, and I was ready to go. And here I was, I'm on site. I've got perfect weather. This is going to work out great, and I don't have some of my equipment. But the next morning, I kind of pulled myself together and kind of took stock of what I had. So I had a Meade ETX optical tube assembly. So I had the tube of my telescope that I had taken on as a carry-on. I had the filter, the solar filter for that telescope, good. And I had a 40mm eyepiece. So that was pretty lucky, because if any one of those three had been missing, I would have been toast for telescopic observing. And you need the telescope, you need an eyepiece, and you need a filter. So that was good. So that didn't close the door on optical, at least. So I was lucky in that sense. I did have the notebook computer, and I did have the planetary imager camera, which was the primary little video camera in those days that I was going to use to try to capture it. But I didn't have some of the connecting wires. So what was I missing that was sitting in Cairo? My tripod for the telescope, that's a problem. The equatorial mount, the electric motor drive for tracking the sun during the transit. I was missing the wires to connect the camera to the thing. And I had another digital camera. This was pre-DSLR days, but I had another digital camera I was going to use. That wasn't so critical, but not having the tripod, that was tricky. So time to get a little bit innovative and try to snatch victory from the jaws of defeat. So I found the IT guy in the resort, and he loaned me a USB cable. So now I was in business. I had the laptop, and I had the little planetary imager, and I had the USB cable to run it. So in theory, I was in gear for a little bit of photography at least. There's the telescopic stuff that I had in my carry-on, so that's good. So I went to the beach, and I thought, well, how am I going to do this without a tripod? So I made a huge pile of sand, and then I in Egypt made a huge pile of sand on the beach, and then I took one of their little beach tables and just kind of pressed it into the top of the pile of sand. And remember, it's the sun's going to come up right on the horizon. It's going to rise with the Venus already on it. So initially, that table was perfectly horizontal. I just had the ETX tube assembly pointed right at the sun, lying flat and just pointing right at the sun. All so far so good. But then as the sun would come up, I would just every few minutes I would just push down a little bit on, and I figured out I figured out which legs would do it. And so after a little bit of practice, I figured out that if I just push these two legs just a little wee bit every 5 minutes, and a little bit of adjusting with the I'll be able to kind of track this thing. And it worked. It worked. So it worked. By the time I was done, though, the table was about like this, and the telescope, everything was trying to slide off. So anyway, under those conditions, I tried to take some pictures. So they won't be very impressive. But this is the view of the schematic for that particular transit. And so it was going to cross at the top of the limb from left to right. I would be seeing the last couple of hours as the sun comes up here. I would catch these last couple of hours, and then Venus would sweep off the disk. So here's a little drawing that I made on site on that little plastic table. And so this is me just capturing at certain points, and if there were a few sunspots, I'm a horrible artist, but this is just me capturing visually what I saw through that eyepiece. And you'll notice the orientation is a bit different than it is for this, and that's because the ETX has an inverting prism for the eyepiece to give it a 90-degree. And so what that does is sets you correct north-south, but east and west will still be reversed. And so if you take this drawing, if you can imagine flipping it top to bottom, so flipping it east and west, you'd flip it top to bottom, and then this row of Venuses would be kind of like on this angle. And then if that's where north is, then you're getting much closer to what this is, north with a row of Venuses there. So that was what I did visually. And then photographically, this was the best one I could do. So keep in mind the conditions I was shooting under. The planetary imager I could get about 15 seconds maybe with the imager before the sun would move out of the field of view of my tabletop tripod. So I did a bunch of little 15-second exposures. It's not a great camera by today's standards, that's for sure. And then I just stacked the best images and sharpened it as best I could. But of course, everything I did was really tough because the sun's moving constantly. I have to keep adjusting the table, and then trying to focus, trying to get a good focus when you have to constantly keep reorganizing the table to stay tracking with the sun, and then only getting 15-second shots, but not bad. So I managed to capture Venus here as it was approaching the limb to finish off, and down here a sunspot in kind of reasonable focus. I was pleased for what I had managed to pull off without having a tripod. And then this is just a little collage that I made just to commemorate the event, a little drawing here and where I was in Egypt. And then here's 5 of those shots that I took right near the end as it was approaching third and fourth contact. So I think third contact was at 6:38 Egypt time. And so here's a shot I did at about 6:37, and here's a shot I did at 6:39. So that's about right. So third contact would have been somewhere in between these two. And then here you're well past third contact. And at this point, I was just kind of overcome by a sense of kind of, this is a big deal, right? This is the last time I'm going to see Venus, transiting the sun. So I put my pencil down, I put the camera controls down, popped the eyepiece back in, and then I just watched it. And I just watched it sweep off. I thought, I'm going to watch this thing sweep off the disk with my own eye, and because it's not coming back for well over 100 years. Now, so a little bit of indication. So back in England, sure enough, cloudy all day long. And so my club members back in the UK that were hoping to get a look at it, didn't happen. They would have only seen an hour of it, and it was cloudy for that whole period. So this time I was vindicated for traveling all the way to Egypt to see it. So here's three books. The Transits of Venus by William Sheehan and John Westfall. That's a good summary. This Chasing Venus book by Andrea Wolf is a fantastic book. It goes into a lot of detail about all the expeditions that happened and all the hardships that people went through. One guy, a French guy, I forget his name now, but he went to the first of the pair, got rained out. Then a whole bunch of wars happened. He had to change countries a bunch of times. Europe was in constant turmoil, but he decided instead of going home, he would stick around. So he basically waited 8 years to catch the second one, and he got clouded out then too. And then by the time he got home to France, they had assumed he was dead. His estate had been sold. All of his stuff was gone. his wife had moved on and married somebody else, and you know, so some of these stories are incredible. But that's a really, really good book. And there's a book about Jeremiah Horrocks too, and their experience on the first one. So that's all I got for you.
The 4-night astronomy course that we run at Riverwood. This is one of about a half of one of the nights, I think. There might be 3 talks given that evening, but so we do moon that night. We do observing the moon and solar eclipses and one other topic, I think. So I'm just going to run through quickly the stuff we cover. I'm not going to bother with most of the details because it's getting late anyway. There are a few cute visualizations that I found that I thought you guys would enjoy. So we cover the origin, the fact that there's a far side and not near side, all the various obvious physical parameters, and we finish off talking about various kinds of lunar software that you can use. This is really nice, just a quick video. It probably won't record, but that's okay. This is a NASA simulation on a supercomputer of the collision of Theia. It's a sort of a giant collision hypothesis. So we start off with Earth being about 90% of the mass that it is now. It's hit by something about the size of Mars, and you can see it does a number. But all this results in the formation of the Earth and the Moon about 10 times closer than they are now. And they figure that the Moon would be roughly in its final orbit and obviously molten, but in its more or less its shape in as little as 6 hours, which is pretty remarkable if you think about it. So I'll stop that. So I have the site if you're interested, but it's the NASA's Scientific Visualization Facility, which is really quite neat. So we talk about the physical parameters, size, and the fact that it's 1.2% of the gravity or the mass of the Earth and 1/6 the gravity, as anyone that watched the Apollo moonwalkers will know. The fact that the orbit varies in distance from the Earth, and the fact that the most distant is the apogee and perigee is the closest. And the fact that it averages 3.8 centimeters each year further out. So that is a to-scale representation. So that is the actual size to scale of the Moon, and Earth on the left and the Moon on the right, and then the actual distance. And a very cute visualization of the year 2022, so last year, and watch the Moon on the left. The Earth is static in this view, but static, but it's rotating, and it's of course NASA, so it's all true visualization. But watch how the Moon comes closer in its perigee and apogee. It's coming closer now. So this is a month cycle, of course, and you get the actual scale and what the difference is, which it's tough to visualize this kind of stuff because it's so far apart. You don't think of it that way, but yeah, the actual I have the actual distances, but yes, on that order. Yeah. It's a cute little I gotta stop that somehow. Okay. So we can see the difference in color is primarily the fact that the perigee picture is taken at a much lower, but normally the color would be more or less the same. But you'll notice the altitude on the one on the left is 77.8. I wish that would go away. There. Whereas the one on the perigee is much lower. As you guys probably know, you can't really detect it visually because it's like 2 weeks apart. Well, okay, yeah. Yeah. Well, the interesting thing is if there is an apogee and it's on the horizon, it looks bigger than a perigee that's up above because of, yeah, anyway. We go through the fact that things are not perfectly aligned, that there's, here we can see that there is an inclination of the lunar orbit to the Earth's orbit around the sun, and that's why we don't have eclipses every month, because sometimes it's above, sometimes it's below, and it's only occasionally that it happens to be in alignment. And we now know, don't we, how far it is, and so up and down means it's pretty rare that it's actually in alignment. We go over the fact that the near side is quite different from the far side, first seen in 1959 by the Soviets. And the reason for it being that it's postulated, at least, that the moon, when it was first formed, was molten. It cooled much more quickly than the Earth. The Earth was much more massive, but the Earth stayed very hot, 2,500 degrees or so, during the cooling of the moon. And so that kept the portion of the moon that was facing the Earth, tidally locked to the Earth, kept it hotter. And so the crust formed much thicker on the far side, something like, I don't remember the number, but there, you can tell it's like 32% Mare on the side facing the Earth, and the far side only has a few percent. Okay, so we talked through the various physical features, visible features of the moon, and point out Tycho, which is a pretty obvious crater, and the fact that Tycho has these rays. Talk about impacts. We mentioned that the the moon is lit from the sun, and so we show them this lovely picture that I'm sure Randy did. Randy was the originator for most of these and did not give attribution for many of these photographs because he's a thief. No, yeah. But it's been probably 15 years now, and the person that did it is dead. So that's okay. This is just basic geometry of things in alignment and why we get a new moon and why we get a full moon. Earthshine. Did you know that Earthshine, if you were able to concentrate all the light from Earthshine into one spot, it'd be about as bright as Venus. However, it's spread out over the size of the moon. So, you know, it's yeah, there you go. Yes, yes. And that is the Earthshine. That's from Apollo 11. Lovely picture. That one they were probably planning. I do not know, but I suspect they were. It took a long time for NASA to figure out that photographs and movies and videos were important. They bring interest. Anyway, there's last man on the moon until a few years from now, probably. Gene Cernan, that was their first EVA. We go through basics, side facing us. This is a little clearer, I think. And here you can see, of course, Tycho with the lovely rays coming out, and talk about the ejecta and all that sort of stuff. Those are the all of the Apollo 11 landing sites, and to give specs on the times and all that. That's also from the, it's from the LRO site, the Lunar Reconnaissance Orbiter. And finally, because of the LRO and a Chinese Chandrasekhar, I think it is, orbiting missions around the moon, we can actually get visual confirmation that yes, indeed, they did walk on the moon. You can see actual foot paths. The a few, I think three of the Apollo missions or so, put ALSEP equipment, so scientific equipment out. They walked it out. You can see a fair distance. And the idea was that, well, you'll see some of them later, detecting moonquakes and the like. The final parking spot, they can see the final parking spot for the lunar roving vehicle, the little car that they had on the moon. They positioned it there so that they could get a shot back of the launch of the liftoff of the final Apollo 17. That is Aldrin carrying the seismic, as I said, detecting moonquakes, and a laser reflecting panel on the right-hand side. We had a talk about, I'm guessing 12 years ago, something like that.
Yeah, fellow who worked with Bendix
who actually developed the, there's a, not a close-up, but so it's a panel of, I think, 64, don't take my word for it, little reflectors that will reflect light back exactly 180 degrees back to where it came from. So they point it roughly at Earth, and you can shoot a laser and time if you watch The Big Bang Theory, you will have seen an episode where they actually shot a laser and got the bounce back. So they can detect they can measure the distance to the moon to within a couple of millimeters, something on a millimeter scale anyway, based on the timing. We go through the names. These are primarily indigenous names for full moons for each month, and the fact that a blue moon. Okay, yeah. Anyway. Yeah, I see it all the time. That's funny. So observing the moon, we can use naked eye, binoculars, telescopes, or lasers, because as I say, they do measure the distance that way. Talk about lunar halos. That's another thing you notice if you're observing the moon and you're lucky enough not to have total cloud cover. The halo is caused by high ice crystals in high cloud cover at a 22-degree angle because of the structure of the ice crystals. We talk about how Westerns talk about man in the moon. Some people see. Buddhist and Native American cultures talk about a bunny on the moon. That's the drawing on the left-hand side. The fact that both Buddhists and Native American have a common visualization of something so weird. We wonder whether it was brought over when they came over, or whether it's just obvious to anyone that looks at that. It looks like a bunny. Looks more like an ant to me, but anyway. Okay. We talk about libration. This is a nice visualization that I found that shows the moon again doing that distance thing, but also showing more than just one face to us, because as it goes further out, it gets a little behind in it's rotating at a constant rate, but the orbit, of course, is non-circular. So we can see about 55% of the primarily the face facing us. And here are a couple of shots of Endymion right at the edge, and then quite a bit further in. So that's that particular mode. And there's another one here of the southern terminator where you can see a pretty substantial, 59? That was 55, but okay. We talk about occultations. I think this one is, correct me if I'm wrong, is that Saturn in 2001? Yeah. So again, much like Kirby talked about with occultations, this is the moon occulting something. And so you can get Saturn, the orbit's pretty well known, but a star or something else, you can get data from it. And you can get mountain height information from this sort of stuff. I assume that's your shot, Randy? Yeah, there you go. And that is a really nice sequence of a very close graze. Yeah, normally I'd buzz through, but that's too nice. In fact, there are two different types of eclipses. if any of this interests you, you'll have to take the Riverwood course. Talking about why we have eclipses, and there's an umbra, which is the total, and then the penumbra that is partially. Here's a really nice Fred Espinac again. Mosaic of an eclipse from not certain what year it was. Okay, well, it's 2000 anyway. Showing, oh, okay. This one is 2014, I think, April, and showing how the moon is not going through the center of the umbra. So the shadow of the moon going out, it's a little low, it's descending. This is our next one. This is our next total in 2025, March 14th. So get your calendars. Another descending one, similar, but you'll notice it's on the northern portion of the umbra. And some apps that you can use for either viewing, or many of us use Heavens Above to find out when ISS or the Chinese space station are going by. Sky is one of my favorites for Android visualization, and Stellarium is available on both. And then we go into other stuff. So I assume there are no questions, but because you probably know it all.